So let's continue. And now we look, before we looked at how we model how the beam is going through and what we can see from the images and try to get an idea if we can or cannot use it for segmentation or any quantitative analysis. What I'm going to switch to now is the data science approach on how to do the analysis and segmentation. And just to run that one. So one topic that is where segmentation is interesting is to identify mitochondria in microscope images like this one. And this is a data set that is in the EPFL open data collection of test data. It is, I think, it's 160 microscopy images which have been labeled, each for training data and for test data. And you can download them. I think each pair is about 200 megabytes, so it's not so small. But our task here is that we want to, from this image, tell that this region is actually a mitochondria, and it should be marked up like this. So this is the information we have. So we have measured and we have some ground truth. And that is our task. And we will actually work with this data a couple of times. Also next week we're going to come back on this data. And when we look at this problem, we have 4 different outcomes, how the values can be assigned. So we can have the true positive. That means the mitochondria are correctly identified. True negative, the pixel is classified as a background pixel correctly. And those are the ones we want to have, so that's why green. And on the other side, we can also have false positive, that some pixels, and you can see back on this one, that you have gray levels that are very confusing. This is about the same as that. And you could have misclassification, saying that also this thin line is the mitochondria. And that would be the false positive. False negative would be when you're inside and you can see that there are some little bit darker regions. I don't think they are sufficient to give a false positive, but anyway, it could be that they are classified as background, and then you would have a hole within the mitochondria, and that would be the false negative. So it's said to be a background, but it's not. So let's try our first segmentation. Very simple. We look at the image, we compute this histogram, we can see the gray levels are distributed. You can see 2 peaks, and these 2 peaks should, in principle, say that we have 2 classes, a foreground and a background. And the thresholding would be that we just put a line between them and hope for the best. The outcome of the segmentation that I did here is I set the threshold at 52, 0.52. And then I got this, and as I said, all these thin lines, they have about the same gray level as the mitochondria. All these are actually also classified as mitochondria. So we have a lot of misclassifications here, in particular if you compare to the true label. So this seems to be not to be the right choice. So let's see what we can do, or how we can analyze the outcome. And now we can look at the performance of this thresholding. We can see we have true negatives. That's all the white here. That's the background. We have the true positive, and we can see using the mask. Actually, this analysis is based on our ground truth, that we know where we have things, and then from there on we can do our investigation. So all the white here means that it's everything that is classified as a background, and it's quite a lot. And then we go into the other side here. Then we look at the true positive, and we see that quite many were okay actually within the mitochondria. However, if we look at the false positive, we see that we have a huge number of misclassifications for false positive. False negative, less so, as I said. The gray levels are not low enough to provoke a false negative in the same sense. So let's take this into the confusion matrix that we looked at in lecture 2. Here I have created this support function that I call show heat map, and it computes the confusion matrix for us and also gives the results in fractions. So we see that we have these colors, or it's actually colored for how much you have in the different classes. And the other thing that I also did is to, whoops, now let's see if I can get down here. Yes. The heat map that I made is actually color-coded for true positive, false negative, and true negative. So what we want is white and black, and the blue and the red, pink, they are the ones we don't want. And then you can, with this map, you can see better what the performance is of this segmentation. So these are nice tools to show the performance. And another way is to start using different metrics. And typically what is used in data science are recall and precision. And recall is, in principle, the ratio of detected versus the expected ones. And you can see that you have here the true positives, and then you have the true positives and the false negatives. And that would include all the pixels that should have been in the true class. Precision is slightly different. Then you take all the true positives and divide it by the true positives and the false positives. So that is divided by all the actual detected. And that's a different way of looking at it. So in principle, it's just here it's detected versus expected, and here is expected versus detected. And for our case, we can see that the recall is 0.82 and the precision is 0.18. So it's not, in particular, the precision is not very good. You want it to be actually quite high. So that means our segmentation is not the best choice, but maybe the best we can do for now. Another tool which is taking this one step further is to look into something called receiver operating characteristics. And that is something that was developed by the statistics people during World War II when they wanted to detect airplanes in radar images, and or also ships probably. It gave an idea how well your detection algorithm actually works. And right now we played with only a single threshold and saw that it got some recall and precision, but actually the ROC curve tells you the whole story by, so we need to compute some hit and miss statistics for different cases, and then we can plot the table. And then we can start plotting in principle, what you have here on the axis is the true positive rate, so the recall, and the false positive. It's not the precision, but it's actually looking at how many misclassifications you did. And those together will actually plot a curve when you play with or scan the threshold in your image. Ideally, you would want to have a curve, RSC curve, that more or less just goes steeply up to 1 and then it stays at 1, no matter what kind of threshold you use. What you usually get is something around out here in the curve, and the straight diagonal here actually correspond to a random guess. So let's try and see what happens with our histogram when we try it on this data. And we see that when we start scanning with our threshold from the beginning of the histogram, then we can't expect many true positives. And then we increase the threshold, and at some point you see that it's getting better and better. So afterwards you want to try to find the sweet spot where you do the best number of true positives and the least number of false positives. And then you can get curves that looks something like this, and then you can use that as a way to characterize how well your segmentation algorithm is working. And actually this RSC curve is already implemented in scikit-learn, so you can just import it, so you don't have to implement it yourself. You can just plug in the ground truth and then the image that you wanted to investigate your model on. And then we can try applying different filters. We learned last week that filters are good to improve the segmentation performance. So we have here a collection of different filters. So one is no filter at all. Then we have Gaussian filter. We have difference of Gaussian, which actually is a high-pass filter. And then we have median filter too. And you can see here what the images look like when you apply these filters. And then what would you expect as outcome from these images when you try to run the RSC curve? Which one would improve and which one would degrade? So what we can have is, first of all, no filter, of course, has some noise, and you can see there are some fluctuations. If you apply the Gaussian filter, you have less fluctuations. Same also for the median filter. And the difference filter actually most likely give you a quite confusing result, because you don't have the distinct blobs anymore. You are more focusing on the edges. So the effect is that we have no filter is the blue one, and the median filter performs slightly better, and the Gauss filter performs apparently the best in this case. The difference of Gaussian is actually confusing. It's even worse than the random guess for the low thresholds, and then it gets a little bit better, but it's not really convincing result for that filter. So that can be rejected for this purpose. Now we only look at it qualitatively, saying this curve is more closer to the corner, but we can't really tell. So what is used is the metric area under the curve. So we do the integral of the area under each of these curves, and then we can get a single number to tell how good these RSC curves are. And again, we said that the Gaussian filter was the best, or the one that seemed to be performing the best. And here we have a scalar number that actually confirms this. And well, the score for the difference of Gaussian is definitely significantly less than the other ones. So this is a tool that is used a lot as a cross-check for different segmentation algorithms. Also, it's part of the evaluation, one of the options for the evaluation of deep learning algorithms, where they actually check against this one. A problem that comes up is until now we have only said we have foreground, background, is material, not material, or something. In many real images, we mostly have many faces. I mentioned in the body, we have organs, we have muscle tissue, we have bones, etc. And that is actually giving you different gray levels and also different regions you want to segment in a good way. And then we come to the problem of segmenting multiple faces. Here is an example of from geology. It's some kind of shale. So you have clay material, you have rock material, and you have voids. And well, this more or less looks like a salt and pepper noise, but it's actually a measured image, and it's really containing relevant information. And here we want to know what we have in the image, starting looking at the histogram. It doesn't really give us so much hint, so we have to go stepwise forward. What we can tell is most likely that all these white spots, they belong here in this part of the histogram. The large grayish background is likely to be in this region, and then you have the dark regions, and they are more likely to be down here. So we can do this preliminary identification, and let's try to do a multiple segmentation. So we have voids, they are below 0.3. Clay is said to be between 0.3 and 0.5, and the rock is above 0.5. And that can be, of course, written, and we can see the segmentation result when we do this. And that would be a way to separate the three classes, but it's not really safe. This is okay. I would actually like to point out some more things about multi-phase segmentation, but I think that comes next week, actually, because there are some problems related to this multi-phase segmentation. If you look at at the histogram here, you can see that there most likely are overlapping classes, and that gives you also a reason for getting misclassifications. And that I apparently didn't have today. Yeah, so let's continue with the implementation of thresholding. So the thresholding as such is in principle one-to-one mapping. You have some input image with the threshold parameter, and out comes another image with a black and white. But how to implement that in different programming languages? Starting with Python, and particularly using NumPy, it's quite easy to do the thresholding. You just say you have your gray level image greater than a threshold, and then you get your thresholded image. Then you get a black and white. If you do a more complicated, like the one with multiple phases, then you can write it something like this, where you have several cases connected with the AND operation. If you don't have NumPy, which is today quite rare, then you have to write some lambda mapping function that does the mapping for you. So that gets a little bit more complicated. So mostly what you do is import NumPy and have that function. This very nice way of writing it has something behind it. And if you look at other languages like Java or C++, then you have to do it in the form of a cascade of for loops. In this case, it's even so advanced that you can say that within some given region, some window, you want to do the segmentation. So you start at x min and max, and you do the same for y and z. And then you compute some offset and address the points within the array, a large array, and do the thresholding per pixel. So you have, with this approach, you really need to go through every pixel one by one through this loop. And same goes for C++, essentially looking the same. So that's not a big difference here. But in these languages, you really need to go step by step doing it. Modern C++ standards, they have similar tools, like you can do it in Python, but that's beyond what I'm going to talk about in these lectures. The alternative solution is, you saw here, that actually the array is just a one-dimensional array. It's not indexed as a three-dimensional array. That's actually computationally really inefficient. So we only have a big array. And that means if you are going through the whole image, you don't have to do it in 3 loops and doing this offset calculation. But instead, you can just have a big single loop that goes through all pixels one by one, because the thresholding doesn't know anything about the neighbors of the pixel. So you don't need to know if it's an X, Y, or Z coordinate. So then you just go through a big chunk of memory. Yeah. What we have gone through now is mainly that with the help of the tools that are used a lot in the data science, we have got a toolbox to validate and check how good the performance is of our segmentation. But in order to do it, you need a ground truth. Otherwise, you can't tell if it's a true or false positive. And if you have multiple materials, of course, then you can also use multiple thresholds. And yeah, the segmentation can be done in different languages, in different ways. You can, by the way, also do the C++ way with Python, if you like, but it's very inefficient. So I'm switching the topic a bit now into something called morphological image processing. And the reason why I introduced this is that the segmentations are rarely perfect. You can expect that they're not perfect. And you can also see it on the confusion matrix that it didn't really make sense in all places. The mitochondria example was extreme, but I'll show you some other cases later. What we do with the morphological analysis is we look at the neighborhood around the pixel to see if this pixel actually is correctly segmented. And it's a set of filters in principle. And that is the toolbox that we often use in order to clean up our images. So let's segment a very noisy image. And this is just a simple model that is a cross in the middle and we apply a threshold, and you can see that that wasn't really what we wanted to have. And now we want to clean it up. Probably first step would actually be to apply some denoising filter to improve the thresholding, but still you would have some misclassifications. So what we do is we apply some filter and looking in the neighborhood around the pixel, and you get more conclusion if you have a large neighborhood, but you can also have more computational cost and possibly also more blurring, so you may smooth relevant small features. And the other side is that if you have a small neighborhood looking around, then it's of course faster, but it could also be that you miss some misclassified features, and that is a balance that we have to play with and see how it works. And these neighborhoods, they are used. We already saw them actually in the convolution. That's the convolution kernel as a neighborhood we have for the morphological operations, which I'm going to talk about now. And then we come to topics that I'm going to talk in some weeks: component labeling and distance maps, and also image correlation. But in principle, in most cases, when you work with it in Python, or in general, you're talking about a structuring element, and in Python, the word for it is footprint, or SLM for structuring element. I think the new naming is actually footprint. So if you use the median filter, I think you should use footprint as to decide how big the neighborhood is. Different neighborhoods that we can look at. If we have 2D images and looking at the 3x3 region, we can look at the 4 connected neighborhood, which only looks in these directions, so horizontally and vertically. And then you can also look at the 8 connected neighborhood, where you include also the corners and get the diagonal neighbors. So these are the ones that you have in 3x3. Of course, if you go to larger neighborhoods, then you have more variation in what you can do, but these are typically the ones that are worked with in many algorithms and filters. Then you can be more creative. If you have the larger neighborhood, you can have disks, crosses, H-line, V-line, star, octagon. So you can, when you make the neighborhood larger, you can be more creative in the shape. And which shape you take also depends on what you want to achieve. So for example, the cross and lines, they would be more suited to detecting crossing points or lines in some directions. So they would actually emphasize those directions. And the other ones, the more blobby ones, they are more to cancel misclassifications in the neighborhood. If you go to 3D, we have more variations in what the neighborhood could look like. So we have the 6 connected, which also goes up and down, except for horizontal, vertical. And the 26 connected is the full cube. And then there is also in the middle, which I don't have here, the 18 connected is also used, and that is when you cut all the corners, then you get 18 connected. Which you use, again, depends on how much information you want to include in your filtering, and also computational efforts to do it. Now we come to the morphological operations, and the 2 basic operations you have in morphology is erosion and dilation. And the erosion is as if you peel off a layer from the object. If it's in 2D or 3D, it's like you peel off a skin. And the dilation is as if you coat the object with an extra layer of pixels or voxels. And these are very helpful. What they do is they can help us to clean up. And if you look at here, the original image is this one. So it's just some shape I made up. And if you erode it, you take out, and by the way, I must say, I used the structuring element, which is a 4-connected 3x3. So here we look at different regions where we can match this shape. And the outcome is the erosion, and there were not many locations in this structure that actually matched that pattern. Dilation, it's growing the object, and here you can see that there are quite many, that it's getting a lot fatter. It's even filled out the gaps here. Even the hole in the middle was filled out. So what you can use them for is essentially if you have false positives, then you can use erosion. And if you have false negatives, then you can use the dilation, in principle. Here I am showing a little bit more in detail what is going on. So this is first the dilation, where we have this cross again. And every time it sees a pixel, then it paints in this cross. And then you can see all this greenish pixels. They are added because there was a hit. And then the result is this one. The other way around is that we have the original, and then with the erosion, if you can fit in this cross, then you will get a pixel. So in this place, you have all the neighbor pixels are in, then we get the pixel. Same here, but not here, because then you have up and side left are not fulfilling the criteria, and that's why you don't get the pixel set to white here. Now I already said that you can use one to take the false positive and the one to take the false negatives, but the cost, as you see, is that you actually also reduce your structures quite a lot, and that is something you don't want. So that is why there is a new set of operations which is called opening and closing, and they are cascades of the erosion and dilation for the opening and the dilation and erosion for the closing. So what is happening is in the opening, first it erodes to take out all the small pixels, and then it grows back again with the dilation. Of course, it's not the perfect shape, and this very thin shape may lose some structures, but anyway, it's turning out better than it was before. So here we do an example of the original going to closing, and you can see all these gaps, also the hole and the bridge here, the channel here and the channel here, they're all closed, but the original shape is actually maintained pretty well. With the opening, the performance is in this case not so good. You get a little space invader and a cross here. But anyway, you have at least the two base structures are at least here. This one was lost. And also all these extra branches around it, they were also lost. So here is also again a close-up of what's happening. So if we do the closing, first what we do is going in the blue. And that is the effect of the dilation, and then coming back after the dilation we do the erosion again, and what is remaining are actually the base structure plus these green areas. So this is, wait, that one must be wrong. Okay, no, that shouldn't be there. Okay, looks strange. Okay, I have to check that one. No, wait. No, it's true, it should be there. Sorry. Yes, so that is how the closing works. And here we can also again see how it works with the opening. So first we erode the whole structure, then we only have the yellow ones left, and afterwards we do the dilation, and then we can see that it fills out a little bit, at least, of the previous structures we had. And there are even more operations where you can start using so-called top hats, where you do an opening or a closing combined with a subtraction of the original image. And these are very useful. For example, if you have badly illuminated images which has an inhomogeneous background, you can actually correct for that, even if you don't have the reference image. So here is an example of how to use it. This is a cell colony, and you can see that there is a gradient in the background going from bright to dark here, and that is quite tricky to handle if you want to put a threshold on it. And I can show that in, let's see, no. Let's see if I can. I think I need to do some executions here now. No, let's try it anyway. So here we try doing a morphological operation. So we have a structure element, which is a disk 15. And then we do the dilation, erosion with the cell image with this structure element. And then we subtract it, so we have the top hat white and top hat black. So it's just the two opposites of each other. And we can see what the effect is here. The white top hat looks pretty weird. I don't think we can use it. Yes?
Before you doing it on a binary image, so how does it work on this?
Yes, so the gray level, that is actually something I didn't mention. Yes, so what erosion and dilation are if you work on gray levels, it's a local max and a local minimum filter. So they are in a so-called class of filters called rank filters. So you have the max is the dilation, the min is the erosion, and in the middle you have the median. So you sort all the pixels in principle, and then you can use the rank filter, and these are the extremes and the midpoint. Yeah. Yes. But however, if we look at the black top hat, you can see that from having this gradient, you have now improved the image into having a flat background, and then it's much easier to segment. It's unfortunately flipped here, but that's an easy thing to. So the intensities are flipped, so the cells, they are now bright instead of dark. But that's an easy operation to correct for. And if you look at the different top hats, you can see that the original looked like this. Then you had the white top hat, which was really confusing, gets a much wider histogram. And the final one, it's probably difficult to see in the light today, but that one has a better tail, and you can even see indications of a little bump that you can segment better. A problem when you do segmentation is partial volume effect. It's if you measure things and they're very small, or also around the edges, you may get strange effects, in particular if you are not perfectly on the pixel as itself. So it's actually a sampling problem. And that can make it hard to segment correctly. So if we look at these, here is if we have small objects like this, 10 pixels, then you can see that the volume fraction that we segment is 32%. And if I increase the radius, meaning actually I work with higher resolution and more pixels, we see that the volume fraction actually is increasing all the way up to 44%. At some point, it doesn't matter how much you measure, how many pixels you get, because then you're down on the very detailed level. So the improvement is in the beginning quite rapid, and then at some point it levels out to some asymptote where it doesn't matter more how many pixels you use. So this is actually something you have to be aware of when you start selecting which pixel size and resolution you want to work with, because at some point when you want to measure the volume, you can make pretty large errors in your measurements due to too large pixels. If you go to spheres, here I did an evaluation where I had first the discrete sphere over the volume of an analytical sphere. So I took the same radius using the equation of the sphere and compared it to the segmented discrete sphere. And if you have just radius 1, then you get this three-dimensional cross, which is not really looking like a sphere. And with increasing radius, it starts to look more and more like a sphere. And here you can see that the volume error for the small radiuses is pretty high. You're up to 50% or something. And not until you come down to 10% radius, you start having something that is about 1% error in the volume measurement. So to really do exact measurements, you need to be aware that you need sufficient pixels in your analysis. And of course, it's a logarithmic scale here, so at radius 20, you're down to a tenth of a percent, so one per mil error. So the effect is really tapering off a lot when you have larger objects. This is just a simple object, a sphere, but if you have more complicated objects, this is getting even more tricky to really quantify how much your error is. But it's at least something you should be aware of when you start doing segmentations. And in some cases, what some people do is even they try to do a modeled refinement of the object in order to get better precision of the volume measurement. Here's also an example of rescaling. What happens if you start downscaling your image, and then in principle the same thing happens as we saw before with the image, but now when you do the rescaling, there is a little sampler actually involved, and what you can see is these little thingies here, it's getting gray. So you get intermediate gray levels in your black and white image when you start downscaling. And they can be more or less dominant. So in some cases you really see them a lot, and in some cases not at all. So also that is something you have to be aware of, that what is happening in principle is, let's see if I can get the chalk, there it is. So if you have something, you have your pixels like this, and your surface is actually going through the pixels like this, the true surface. Then at some point, so here this one will probably be a 1, but that one, it's less than 50% of the pixel is filled, so that one will probably turn into a 0, or something in between, say 0.4. And that is what we see in these images. And that is always the problem when you start doing the sampling in your images, that you never have it perfectly fitting the exact pixels. The pixels is a rectangular grid, and the world is curved somehow, and then you always get in between somewhere. Further effects is also that you have imaging system blurring, which even makes it harder to distinguish exact positions. And that was the end of this part. So we have, again, we have started using the histogram for segmentation. Today, we only looked at manual segmentation, or sweeping all gray levels to see how it segments. We also used the gray levels, the data science approaches, looking at recall and precision, and the RC curve, which are good tools in order to quantify how well your methods are working. And I think you should use them in your test setups. So always when you implement some kind of segmentation, always check how good it actually does towards some ground truth, because otherwise you don't really know how well you are doing. And now the last part is also the partial volume effect, is something that you really need to be aware of. And the larger objects you have, the more precise you can get in your following measurements. Next week, I'm going to talk more about the automated methods. So really, it's selecting just a threshold in the histogram is quite arbitrary, but there is a big number of algorithms to do this, and that is the topic of next week. So, thank you for today.